You ever wondered why salt dissolves so easily in water but oil stubbornly refuses? Or how fizzy drinks keep their fizz until you open them? Also, what about why we put salt on icy roads in winter? For all these questions, we have answers in this chapter. Welcome to the chapter which talks about fascinating world of solutions. Homogeneous mixtures that are everywhere around us, from the air we breathe to the blood in our veins. So let's uncover the secret behind how they work, why they have behaved the way they do. First, what exactly the solution is? Solution is a homogeneous mixture of two or more components. Two or more components combined to produce solutions. How? Homogeneously. Homogeneous means we can't separate it out. Say for example, I'm mixing water and sugar. I'm getting sugar solution. This is a binary solution where it involves only two components to produce a homogeneous mixture. Here, water is our solvent which dissolves a solute, that is sugar. Why it needs to dissolve in particular solvent? It all comes down to energy or randomness. We very well know about thermodynamics chapter. Is it what is delta G, delta H, delta S, everything. For a process to be spontaneous, delta G must be less than 0. Right? So we have the formula, right? Delta G is equal to delta H minus T delta S. Here delta H is enthalpy, delta S is entropy. When the solution is prepared, when we are adding solute to the solvent, first of all, what need to happen? Here we have to understand two things. First one is lattice energy. Is the energy needed to break apart the solute crystals. Energy needed to break the solute crystals. For example, sugar, salt. So whatever the solute you have taken. And the second one is hydration energy. Hydration energy are also called as solvation energy, if that is not for water, is the energy released when solute particles are surrounded by solvent. Okay, it is an energy released. Okay, why this is so important? Here we have two types of solution. First one is exothermic process, where heat releases, right? Heat releases. In this case, hydration energy which should be greater than lattice energy. So the process releases heat and the delta H becomes less than 0. And the process is spontaneous and everything. Say for example, I'm taking some salt like a calcium chloride. When dissolving it in water, I can sense the water turn to be warm. It is a perfect example of exothermic reaction where delta H is less than 0 and delta S is greater than 0. More randomness, is it? Okay. What about the case 2? Case 2 is endothermic reaction where heat is absorbed in the process, which means hydration energy should be less than lattice energy. We very well know what is hydration energy, what is lattice energy. So hydration energy should be less than the lattice energy, which in this case delta H turns to be greater than 0 and this leads to insoluble case at the given temperature. Let's say room temperature. Okay, you might have seen some solutions are not dissolving in water. While we are heating it up, it will get dissolved. Right? Think of a dissolving ammonium nitrate. ammonium nitrate, when we are dissolving it in water, we can feel some kind of chillness around the beaker. It is because it is absorbing the heat energy from the surrounding. For such processes to be spontaneous, we have to take delta Ts have to be modulus. Okay, so in that case, delta H value should also be modulus. So this process will become spontaneous. Okay, so now we understood what is the effect of temperature in exothermic and endothermic cases. What is that? For exothermic, increase of temperature decreases the solubility, and for endothermic case, increase of temperature increases the solubility, and vice versa also. Okay, we understood the effect of temperature. Next, concentration. Why that is so important? Because to know about the solubility, we have to know the concentration. What are the concentration terms we have? We already studied in your 11th class about the concentration terms. The first one is mass by mass or weight by weight percentage, which measures the mass of the solute as a percentage of total solution in mass. Right? Say for example, I'm having 20 grams of NaCl in 80 grams of water, which means 20% mass by mass. Okay. The second one, I'm just going through this briefly. We already know about these things. Okay. Then the next one is mass by volume or weight by volume. Mass by volume is the measure of mass of the solute per 100 ml of the solution. Let's say 20 grams of NaCl in 100 ml of solution. And the third term is volume by volume, in which, in this case of liquid-liquid solutions. Previously, these two cases were solid and liquid, solid and solid, and solid and liquid. This is liquid and liquid case of solution. Okay, so volume of solute per 100 ml of solution. Ma'am, I need notes for this. I don't have 11th notes. Don't worry, which will be uploaded in our website. You can easily download it for free. Okay, don't worry about the notes. I'm not having those lines, nothing. Okay, just to concentrate. Okay, then next very important concentration term is molarity. Molarity, which is denoted by capital M. That is moles of solute per liter. Moles per solute per liter. It is a temperature dependent concentration term. And what is temperature dependent? As we are increasing or decreasing the temperature, the concentration will get affected. Okay. Then the next one is molality. Molality, that is denoted by small m, that is moles of solute per kilogram of solvent. This is temperature independent concentration term, which is not affected by increase or decrease of temperature. Okay, then the next one is normality. Normality, that is gram equivalents of solute, per liter of solution. Talking about normality, which is denoted by the symbol capital N. Okay, it is also similar to molarity. This is temperature dependent concentration term. Okay, then the seventh one, most important one, that is mole fraction. It is the ratio of moles of one component to the moles of all. Ratio of 1 to all. Okay, so let's say I'm taking A and B as a component. Now, why are you stressing mole fraction more? In this chapter, we are using it more. Let's say I'm taking component A and B. For mole fraction of A, I should write it as Na by Na plus Nb, which is number of moles of A divided by total number of moles. Similarly, if I want the mole fraction of B, Nb by Na plus Nb. And point to be noted here is the total mole fraction always equal to be 1. Let's say I'm having two components, then chi A and chi B equal to 1. If I'm having 3, chi A plus chi B plus chi C equal to 1. So no matter how many components you have in the solution, the sum of all those mole fraction which will be equal to 1. And also from there you can get the word that will be the mole fraction you are calculating, that will be always less than 1, 0.8, 0.72, like that. It will be always less than. Okay, so whenever you are doing calculation, this will help you. And this is a temperature independent term. Okay, so now we understood basics of solutions. Let's get into the concepts. The first thing is we have to understand vapor pressure and boiling point. What is boiling point first of all? To understand boiling point, we have to know the vapor pressure. So what is vapor pressure? Imagine a liquid in a sealed container. Okay, liquid in a sealed container. Some liquids can escape into the air above it to forming a vapor while we are heating it. So I'm going to heat it. While heating, what will happen? Since this is a closed container, it can't escape outside to the surrounding. It can't escape to the surrounding, but these vapor particles can be here mixed with the air inside the container, right? So that will create certain pressure to the existing solution. The pressure excreted by the vapors on the liquid surface, which is in equilibrium, that is called our vapor pressure. So the pressure excreted by these vapors are vapor pressure. Okay, but why this is so important? This pressure is an independent of the container shape, container size. It is only dependent on temperature. It depends on temperature. As we are increasing the temperature, what will happen? More the vapors will be produced, more pressure it will create. Yes, I'm coming to that point. Why that is so important? Because when the solution will reach the boiling point, when the vapor pressure equals to atmospheric pressure or external pressure, then only the liquid start to boil. That point only we are measuring that as a boiling point. Okay. So boiling point is the specific temperature at which the vapor pressure becomes equal to the external atmospheric pressure. So what if the external pressure is increasing? What if the external pressure is decreasing? Is there any scenario like this? Yes, we have. At higher altitudes, what will happen? Let's say you are trying to prepare your food at higher altitudes, where the atmospheric pressure is very lower. Water will start boil before 100 degrees Celsius because it can easily attain. So the boiling point will increase. So atmospheric pressure increases means boiling point will also increase, and if that is decreasing, boiling point will also decrease. Okay. Then what if the vapor pressure increases? Vapor pressure increases means boiling point will decrease. it can easily reach the atmospheric pressure, right? So the boiling point will get decreases. This is the most important concept which we are seeing in the daily life. Okay, we have seen liquid in liquid and what is vapor pressure, what is boiling point and everything. Now we are going into gases in liquid. The straightforward example is our carbonated drinks. So which gas we are introducing in our soft drink? Tell me in the comments below which gas we are dissolving in it. Okay, here we are going to talk about nature of the gas. That is also playing a very important role. And nature of the solvent as well. The gases can interact strongly with the solvent, which makes it more soluble. Say for example, ammonia, sulfur trioxide, NO2, they are highly soluble in water because they react with it. And in contrast, if I'm taking oxygen, nitrogen, helium, argon, these are some spherically soluble gases which don't react with water chemically, right? So which can be easily dissolvable? Those are reacting with liquids, reacting with solvent easily. That is nature of gas. Talking about temperature effect. Effect of temperature. Increasing temperature will lead to decreases the solubility. Ma'am, how? In case of liquids, you said increase of temperature in endothermic condition may lead to increase in solubility. But here you are saying decrease in solubility. Why? Because most of the cases in gases and liquid, these are exothermic reactions which releases heat. This is why warm soda goes flat faster than the cold soda. Okay, the dissolved carbon dioxide escapes more easily at higher temperatures. And the third very important factor is pressure. Here only we are talking about the most important law, Henry's law. The first formula I'm going to introduce is here of this chapter. First, let's talk about the law. Henry's law states that the solubility of gas in a liquid is directly proportional to the pressure or partial pressure of that gas above the liquid. Okay, Henry's law comes under gases in liquid. Later in this chapter, I'm going to introduce another law, Raoult's law, which is for liquid and liquid. So this is gases in liquid. Okay, I'm telling you the law once again. The solubility of the gas in the liquid is directly proportional to the partial pressure of the gas above the liquid. First of all, we need to understand what is partial pressure, right? So this is the pressure excreted by the gas molecule, each gas molecule. Okay, in simple words, what I can say, let's say I'm having a container of 10 gas molecule and the overall pressure of the container is 10 pascals, which means each one of these gas molecules is having 1 pascal pressure on them. Okay, that is what the partial pressure is. Okay, so how I can write this Henry's law is partial pressure is proportional to mole fraction or solubility, right? So I'm taking that as mole fraction. Number of moles are getting dissolved. Partial pressure is proportional to mole fraction. So to remove the proportionality constant, I have to remove the proportional symbol, I have to put a constant. So I'm going to introduce Henry's constant over here. Okay, this is Henry's constant. They will give you the value of Henry's constant, you need not to worry about that. This means higher pressure forces more gas into the solution, right? That is how they are introducing or dissolving the gas particles into the sweetened water, right? Which is why the soft drink bottles are under high pressure of carbon dioxide. When you are releasing that pressure, the gases will tend to escape. That is what causing the fizz sound. Okay. What is the limitation of Henry's law? Each law, each theory has its own limitation, right? So what is the first limitation? It is for non-reacting gases. Non-reacting gases only. Not applicable at very high pressures and requires only the moderate temperature. Also, the gas solubility shouldn't be too high. Gas solubility should not be too high. This is for non-reacting gases, not applicable for high pressure, and it requires only moderate temperature. So this can be asked as an MCQ in JEE as well. It requires moderate temperature. Okay. Then, now we are going to introduce mixing of liquids. Liquid in liquid. It can be ethanol plus water or any other liquid-liquid solution. When two liquids mix, their vapor pressures behave predictably, described by Raoult's. We already talked about Henry's law. Here we are going to talk about Raoult's law. Raoult's law, which states that in a solution, the vapor pressure of component at a given temperature is directly proportional to its mole fraction. Ma'am, this is very similar to Henry's law. There also they are talking about pressure and mole fraction. Here also we are talking about the same. Yes, that is true. This is very similar to Henry's law, but Henry's law talks about the partial pressure. Here we are talking about vapor pressure. Henry's law is for gas and liquid. Here we are talking liquid in liquid solutions. Okay. Here we are writing the vapor pressure is proportional to mole fraction. Vapor pressure of A proportional to mole fraction of A. To remove the proportionality symbol, you can introduce a constant, that is K chi A. If that is a pure solution, not mixing, before mixing pure component, then what would be the chi A value? Then equal to 1, right? In that case, K will be equal to PA naught. So this is the pressure of pure component. Vapor pressure of pure component. Point to be noted. This is the pure pressure of pure component. So how I am writing this equation is, instead of K, I am using PA is equal to PA naught chi A. This formula is super important. Note this down. Similarly, how I can write for B, PB is equal to PB naught chi B. What about the total pressure? For total pressure, according to Dalton's law of partial pressures, how we can write it? Summing up. That's just sum all those partial pressures, right? So here also we are doing the same. Total pressure, P total equal to PA plus PB. By substituting these values, partial pressure of pure component A plus mole fraction of A, partial pressure of pure component B into mole fraction of B. Or otherwise, I could write it as, here I am having two terms, chi A and chi B, mole fraction of A and mole fraction of B. Let me make it as a single term, because we know that, I'm writing it here, we know that chi A plus chi B is equal to 1, right? So which will be chi B is equal to chi A minus 1, right? So total pressure equal to partial vapor pressure of pure A 1 minus chi B plus PB naught, okay, right? Upon simplifying this, I'll be ended up with, simplifying means just multiply it inside and get the final equation as PA naught plus PB naught minus PA naught into IB. This is also an important equation. So whenever they are giving you the question, analyze it and use the formulas accordingly. So next we are going to post the practice problems of this chapter. So stay tuned. Now we are moving on to the graphical representation of Raoult's law. How we can represent it? For that, I'm going to take this kind of graph, where it starts from pure component of A and ends with pure component of B. So chi A becomes 0, chi B becomes 1, here chi B equal to 0. Okay, this graph is between vapor pressure and mole fraction. Mole fraction of XA is decreasing, XB is increasing. Okay, so now vapor pressure of pure A, I'm pointing this as PA naught, and this one is vapor pressure of pure B, PB naught. So as chi B increases, this is going to reach here, and from here, as the chi A increases, it goes like this. Total vapor pressure will be, so it will be a straight line of PT equal to PA plus PB, right? So this is for PB and this is for PA. Now why this is important? We'll see in a while, don't rush. So here what we have concluded is that as I'm increasing chi B, it is going towards the pure B at total pressure, which is PA plus PB. Okay, what if I'm having both the solutions are in vapor phase? Mole fractions of A and B in vapor phase, because we told you initially, while we are boiling it, it will maintain a equilibrium, vapor to liquid equilibrium. So we have to talk about the vapor phase as well. For liquid phase, we took as chi A and chi B, or XA and XB. Here we are taking that as YA and YB are the mole fractions of A and B in vapor phase. Okay, so which is in equilibrium with XA and XB? How I can write the pressure? PA is equal to YA into total pressure. Similarly, for PB, YB into total pressure. Okay, it is slightly different from liquid phase. Liquid phase, this is vapor phase. What are ideal solution? What is ideal gas which obeys the ideal gas equation, then that is PV is equal to nRT, then that is ideal gas. Similarly, in case of ideal solutions, when this obeys Raoult's law, then that is ideal solution. If that is not, then that is real solution. Okay. So when that have to obey Raoult's law, at all concentration and temperatures it have to obey. So what are the conditions we need to follow over here for maintaining the ideal solution? So the first condition is how it is interacting. The attraction between the molecules A and B should be equal to the attraction between the similar molecules AA and BB. Okay. So the attraction between AA should be equal to similar molecules AA and BB. Then the next condition is delta V mix, volume mixing. The volume change should be 0. There should not be no change in volume while mixing. And the third condition is enthalpy change upon mixing. So enthalpy change should also be 0. No heat is absorbed or released. And the fourth condition is, I'm writing it here. So the fourth condition is entropy change, delta S mix, should be greater than 0. It should indicate the increase of randomness. Although spontaneous process, we have positive entropy, right? Then Gibbs free energy change, delta G mix must be less than 0. Then only that becomes spontaneous. Okay, so what is the classic example for this type of ideal solution? That is benzene with toluene. This is an ideal solution. What about non-ideal solutions? Which are not obeying Raoult's law, those are non-ideal solution. Non-ideal, which is not obeying. Why that is not obeying? There are two types of non-ideal solutions. When that is not becoming non-ideal, that can be of two types. The first type is negative deviation from Raoult's law. Now, what is this? We already talked about the graphical representation of Raoult's law, right? So from that representation, it is deviating. It is not obeying. It shows the negative deviation. Say for example, the actual vapor pressure is lower than predicted by Raoult's law. So the actual vapor pressure is lower. Why that is happening? Because the first case may be the AB interaction are stronger than AA and BB interactions. Okay, in Raoult's law what we said should be equal, right? Here AB interaction is stronger. This means the molecules prefers to stay in liquid phase. It is not going as a gases. Then the second one is volume change. It should be 0 in ideal scenario, but delta V mix is less than 0. And what about enthalpy? Enthalpy of mixing is less than 0. The reaction is exothermic reaction, correct? So what is the example for this type of negative deviation from Raoult's law? Mixing of acid plus water. For example, HCl plus water, or chloroform and acetone. Chloroform, which is CHCl3 plus acetone. These are the examples of negative deviation, where these are having strong hydrogen bonding forms between the different molecules, A and B molecules. So that bond is stronger, shows the negative deviation. So if that is showing the negative deviation, how the graph will look like? For negative deviation from Raoult's law, this is how the graph look like. Yeah. Already we say this shows the lower part. The vapor pressure is lower than predicted by the Raoult's law. So the white lines are the Raoult's law and the yellow ones, which is the negative deviation. Okay, so what this indicates, AB interaction is more. P actual, which is lower than P ideal. This scenario. Okay, then we are moving on to positive deviation. It's quite opposite to negative. When this can happen, first of all, what is this? This is the actual will be greater than the ideal scenario. Okay, so what are the conditions? So the first one, interactions, right? So the AB interactions are weaker than the AA and BB interactions. So molecules are more eager to escape as vapor phase. Then volume change, delta V mix is greater than 0 because the volume is expanding on mixing. It is tend to go as a vapor phase, right? Then the third condition, enthalpy change, delta H mix is greater than 0, which is an endothermic process. Heat absorbed. Right. So what is an example for this scenario? Mixing of alcohol plus water. Guys, example is also equally important. Please note it down. Alcohol plus water, because the hydrogen bonding in pure water is stronger than the mixture one. Then acetone with sulfur dioxide. CS2. Acetone with sulfur dioxide. Or CCl4 also you can take. You have to check whether the question can be asked in the way, out of which of the following shows negative deviation, which of the following shows positive deviation. Okay, so you have to check which hydrogen bonding, which interaction is more. Here you can see it is showing higher than the predicted by the Raoult's law. So the actual is greater than ideal. So the yellow ones are positive deviation. Okay, so now we understood what is positive and negative deviations are. Now we are going to talk about azeotropic mixtures. What is this weird name? It is also called as the unbreakable mixtures. Why is it so? It is acting as a pure component. Although this is a mixture, but this is acting as a pure component. It boils at a constant temperature. So this is a binary mixture of liquids that boils at a constant temperature. Also, whenever we are distilling it, it is not changing its composition while distillation is going on. Okay? We can't separate using fractional distillation. So ma'am, what is fractional distillation? Fractional distillation is a technique we are using to separate two miscible liquids at which are having different temperatures, azeotropic mixtures or azeotropes. The first type is minimum boiling azeotrope. Minimum boiling azeotrope. What is that? So azeotropic mixture means we know. These azeotropes, minimum boiling azeotropes, are formed by the solution that exhibit positive deviation from Raoult's law. We already saw what is Raoult's law is and how it is showing positive deviation. So in simple words, I can say AB-AB interactions are weaker than AA and BB. Right? So that is what positive deviation. These are having weaker attractive forces between the mixed component that will lead to high tendency of formation of vapors. Okay. So due to the higher vapor pressure, these are forming minimum boiling azeotropes to boil at low temperatures. It boils at low temperature. Then either of its pure component. This as in graphs. So here I took the graph between temperature and mole fraction of alcohol is increasing. This type of graph. Here you can see the boiling point of water, that is 373 Kelvin, and the boiling point of ethanol, that is 351.3 Kelvin. Okay. So what we said for minimum boiling azeotrope, it boils at the temperature which is not either of these one, right? It is showing lower than that. Okay, as you can see, the yellow ones are representing the vapor composition and the green ones are representing the liquid phase. Okay, and the dotted lines are showing the normal one, how it should be. Okay, this graph clearly represents at what boiling point it boils. It boils at 351.15 Kelvin. Okay, so this is an example of minimum boiling azeotrope. The next one is maximum boiling azeotrope. It is very opposite to the previous one, minimum boiling azeotrope. These are formed by the negative deviation showing compounds. So which are showing negative deviations? Where AB interactions are stronger than AA and BB. Right? So those are showing negative deviation, that is showing maximum boiling azeotrope. Due to their lower vapor pressure, these azeotropes boils at higher temperature than their corresponding liquids, in their pure components. Okay, so that is what maximum boiling azeotrope. Graphical representation of maximum boiling azeotrope, and the example is acid plus water. No, I took HCl plus water as an example. Here you can see the temperature difference, 188 Kelvin for HCl and 373 Kelvin for water. As I'm increasing the water content over here, what can happen? It is boiling at the temperature of azeotrope. It boils at the temperature 383, that is lower than both of these. Okay, at this point you can separate out A, and this point you can separate out B, and this is our azeotrope point. At this point the solution behaves as a azeotropic mixture.